So in this video, I'm going to be going over a chi-squared example where we're seeing if the normal distribution might be a potential fit for some data. In this particular example, we're going to be estimating the mean and the standard deviation from the data itself. So that means it's going to take away an additional 2 from the degrees of freedom. Okay, so let's get on with it and write our hypothesis first. Okay, so I've written them there. The customer's waiting times could be modeled by a normal distribution, or H1 that they cannot be modeled by a normal distribution. So that's what we're going to test against. Now, in this question, first of all, it's kind of adapted from a past exam question, which was split into much smaller bits. It's unlikely you'd be asked to go, because there's quite a lot of calculations involved. I'm going to talk about how you'd use the calculator, but I'm also going to show how you would do the calculator's longhand without using the stat mode, if that's what you need to do. So first of all, let's just talk about, we need to first of all work unbiased estimators out, because we're going to be estimating the mean and the standard deviation. So estimators for mean and standard deviation. So that's the first thing we're going to do. And in order to do that, I'm going to need to kind of construct a table with these data here. So let me just do that and then talk about how we would use the calculators. You're going to work out the mean and standard deviation first and then take it from there. I've used Excel here, so as I say, it would be unlikely that you would have to do all this longhand without using stat mode on your calculator or whatever, but it's worth seeing what you would need to do. Here, the data, first of all, I need to write in the midpoints. So the midpoint of 0, 3 is 1.5 and so on. I've got a table of frequencies, that's just those. And then I've got a table of frequency times by the midpoint, times by the x, and the midpoint squared times by the frequency, which gives me my values, my summary data, sigma f equals 50, and sigma fx equals to 274.5. And sigma fx squared equals to 1844.3. Okay, so that means x bar is easy enough. X bar is just going to be this number divided by this number, sigma fx, the total of all the data times divided by the total frequency. So that comes to 5.49. Then we need an unbiased estimator for the standard deviation. And remember, this is sample data. We're estimating the standard deviation. So it's S squared using our notation, which is where we basically divide them by n minus 1. Because of the way the data, we've constructed the data, I might just write it like this, just kind of work out the kind of sample standard deviation and kind of scale it to make it the unbiased, so basically times by 50 over 49, and then that will be the sigma fx squared, that's 1844.3 divided by 50, take away this number squared, 5.49 squared. Okay, but the main thing is it's got to be unbiased. It's got to be unbiased, and that involves dividing by 49 or scaling the thing by 50 over 49. So that comes to 6.88. Okay, so that's 6.88. I'm going to store it in the calculator because actually there's 6.88357 because we're going to be using, we're going to be estimating what the numbers are, finding the estimated values next using a calculator. Before I do that, I might just talk about how we would use a calculator to actually work out these measures here, because say if this it would be totally acceptable in this kind of question if you really were to get something like this in the exam, certainly for most it would be acceptable to use the stat mode on the calculator. So I'm just going to quickly show you that. Okay, so we need to be putting these numbers, basically we need to be putting these numbers in our calculator. Okay, we need to be putting them in the calculator, and we need a frequency column. So if you don't have a frequency column, you need to make one because we obviously need frequency. So when we go to, on this calculator, if we go to menu 6 and one variable, because it is one variable, we've got a frequency column. If that's not there, you'll need to go down to stat mode. So shift menu, you'll need to change go to free stat and make sure the frequency column is on. If that's not, in this case, it was on already, so I'll press 1. But if it was switched off, if you want to switch it off, which you do sometimes too, you press 2 at that point. So now let's type in these midpoints. So 1.5 equals 4 equals 5.5, 7, and 10. Let's put the frequencies in. So we have 8, 12, 13, 9, and 8. And now we can go to options, and we want one variable calc, so that's 3. And there we can see we've got our 5.49, which we knew, that's our mean x bar. It's also given our value of s square, our value of s squared. Oh, that just reminds me, we're going to have to, that's the actual variance we have there. So we need to actually square root it, which will be 2.623. So yeah, we've got those. We also have the summary data that we worked out. So our 1844.3 actually was 0.25 more accurately, and our 274.5 are there as well if you need the summary data. So that's how we would use a calculator, and obviously that would then be a pretty quick process. Okay, so now we want to work out our expected values. First thing to notice is that it's an infinite distribution, so it's not going to abruptly finish at 0. I know that you might say, well, this data, it would end at 0, but if we're modeling it as a normal distribution, then we can't have a defined kind of a sudden start or a sudden end to the distribution for the actual model. So we need to actually rewrite the table like this. So almost x, let's write in blue, x is less than or equal to, well, let's just say less than 3. It doesn't really matter with a discrete distribution, but just for consistency, I'll write that one is less than. And this one, this category here, would be between 3 and 5. And so on. 8. And remember, this one now would just be, wouldn't have it again, it wouldn't just suddenly start at 12 there either. So finish at 12. So that's 8, 6, 5. Right, so to work out our EI for example, we need to do 50 because we got a sample, so the number of in our sample is 50 times by whatever the probability is. So, for example, probability X being less than or equal to A, but less than B. So, and we're going to use a calculator to work out those numbers. Okay. So I'm going to put those in the calculator. I'll do 2 of them, and then I'll leave you to do the rest. So let's just bring up the calculator now. So press the menu button, menu 7. So let's work this one out, at least work out the P for now, and then we can just work with the rest later. So we want normal CD. We never use normal PD, so it's normal CD, so press 2. The lower, as I say, we don't really want to put 0 in because it's normal and it's kind of, you've got an asymptote on the left-hand side. So as unlikely, just putting in an unlikely small number, I'm going to put minus 100 in. And we can put the upper as 3. Our standard deviation is 2.623. And our mean is 5.49. So it's 0.1712, and we're going to times that by 50. So now let us do the next category. So again, we press menu 7, normal. Now we've got 3 and 5 in here, 3, 5. And if you're doing one after the other, it'll remember the numbers from before. So the probability this time is 0.2547, and we times that number by 50. Okay, so that's 12.73 approximately. And then I'll leave you to, if you want, you can pause the tape and just check you get the next ones correct. Let's pull that down. So you get the next ones correct. So I'll leave you to follow on, just check that you know how to use your calculator or whatever method you are so that you can get the right numbers here. You might want to pause the tape and just check. Okay, so those are my EI. Let's just put them by side for comparison. We've got 8, 12, 13, 9, and 8. I mean, informally, we can see some of them are matched pretty closely, like at the beginning and the end, but there does seem to be some discrepancy here. So we'll see whether these are close enough match, and using our chi-squared test. And our test statistic for chi-squared test is x squared equals to sigma OI over OI minus EI over EI squared. So that will be equal to all of the, let's just write the first one out. So that's 8 minus 8.56 squared all over 8.56. That's for this row here. 8 minus the we're finding the difference between those two, and then so on for the rest of the cell. Okay, so that's the actual each one individually, and then we'll add them up in a moment. Before I do that, can I perhaps rust into this a little bit? Into this, there was no need to combine cells in this case. So all EI greater than 5, so there's no need to combine cells. You don't need to write that in your solutions. I'm just saying it's something that you ought to think about before you plunge into this calculation here. I just didn't mention it. So need to combine cells in this example. Okay, so let's just write in the numbers. And I'm getting 5.087 There's my x squared test statistic there. And so now I need to look up the relevant chi-square table, but we need to give, I did mention it earlier on, it feels a while back now, but remember we estimated the mean and standard deviation. So we estimated it, so therefore we need to take off a further two degrees of freedom. So the degrees of freedom is equal to the number of elements. So that's 1, 2, 3, 4, 5 after combining, but we didn't do any combining in this case. So that's 5. Take away 1, because we always take away 1 because the last one is kind of fixed after the first 4. And then the take away 2 because both mu and sigma estimated with x bar and s. So we've done both. You could have situations where they ask you to estimate one of them and fix the other, in which case you'd be taking away 1. Or you could have a situation where it said, imagine the question said, test this normal distribution. In this case, you could think it would be quite reasonable if they said test 5.5 and with a standard deviation of, I don't know, 2.6, say. And if it actually just said to test that and fix it, that as a model, then you wouldn't have to take away those 2 extra degrees of freedom. Okay, so let's look up that number in a chi-squared. So we're looking for, because that makes 2. That makes 2. The significance level, 5%. So we want 0.95. So our chi-squared value we're looking for is 2 degrees freedom of 0.95. So let's look up that value. We can see the value is 5.911. Okay, so we can see the value is 5.911. And so we're going to compare that to our x squared value. 5.991. As I say, I always like to draw my chi-squared. It's got only 2 degrees of freedom, so actually it'll look like this, but not that you have to draw it accurately, but it'll look like that. The 0.95 critical region, the 95% critical region, the critical value here is 5.911. But we're here. We're in the acceptance region, not in the critical region. So the critical region, the regions where you would reject H0, it's not in there. So we're there, 5.08 with the 5.087. So we're there. So let's write it as an inequality. So we've got 5.087 is less than our critical value. So the conclusion is do not reject H0. Okay, do not reject H0. And so now, depending on the board you do, how your contextual answer will be, there'll be more kind of stringent with certain kind of specifications than others. I know that OCR are funny about this. They're going to want a double negative in their conclusion. So they will want something like this. There is insufficient evidence to suggest a normal distribution is not a good fit. So it might be that the normal distribution is a good fit, but that's how we don't know that. Of course, you never do with any hypothesis test, but particularly here. So we it's not, and it was about for customer waiting times at the post office. I say you might find other check with turn times at the post office, check with mark schemes or whatever to see what they want there. But OCRA is going to want this double. Well, they certainly did in the most recent example I've seen. They wanted that double negative in their conclusion. There was insufficient evidence to suggest the normal distribution is not a good fit for customer waiting times at the post office. So it might be a good fit. Okay, that's it. I hope you found this useful.